Okay, Thomas, you may start whenever you want.
Okay, good. So thank you, everyone. Thank you for being here. So that's the day 2 of my lecture series, and it, I start with the first half of the course, which is about cluster algebras. And yesterday, after many lengthy preparations, we finally succeeded towards the end to actually give the definition of a cluster algebra. So this is what I put on the slides here. This is the last, that was the last definition of yesterday's lecture, where we finally arrive at the definition of a cluster algebra. So let me go over this again, because as you see, as you have seen, it's a long definition. So we fix we fix the a field of rational functions, which we call f, in variables x1 to xn, and with coefficients over the rationals. And then we need to define a couple of notations. First, we say a seed is a pair of two pieces R U, where R is a quiver, or more generally a valued quiver, with n vertices. So the n number of vertices and the number of variables here need to coincide. And then the seed is given by a quiver and a set of uh, rational functions which are algebraically independent in this field F. Then we need to define a seed mutation. So mutation of a seed at some index k is a new seed r prime u prime, which is obtained as follows. First, we mutate the quiver. This we had discussed in length yesterday. And then second, we need to explain how do we mutate that set of variables. So if we do a mutation at k and we have this set of variables u1 to un, we keep all of them except the variable number k. So we replace only one uk by a new variable uk prime. And this new variable is defined, is determined by the following equation, like in the quiver setting by this equation. So we say that the product of the new variable uk prime times the old variable uk is given by that expression. That expression is a product of the other variables, and which variables do enter this equation depends on how many arrows uh, start in k, the vertex where we mutate, or end in k, tail is a. So that's a formula which determines the variable. If you prefer the matrix notation, this is the same formula in matrix notation, reads like this. Okay, we also, class algebras are defined by mutations. So this is a recursive procedure, but we have to define where do we start the recursion. So this is called the initial seed. Sorry. The initial seed is our start of the recursion. Initially, we start with a given quiver Q and the variables x1 to xn, which we fix from the beginning. So that's our initial seed. And then a couple of more notations. A cluster, I can enlarge this a little bit, right? Yes. A cluster is then one of these sets that do occur in some of the seeds. One of these sets of variables that occur in this iteration of mutations of seeds. This is called a cluster. The cluster variables are all those new variables that we obtain from mutating, that we obtain by mutating starting from the initial ones. And finally, the cluster algebra is denoted AQ, and it's the subalgebra of this field, which is generated by all the cluster variables, by all those UIs. Okay, so this is kind of a lot. I would like to illustrate this by some examples. Um, I'm trying to get back to see if there's anyone in the chat. Okay, good. Okay, good. So let's do some examples. No, I forgot one notation. The exchanged graph is the graph that describes the mutations. Yeah, so the graph has as vertices the seeds and edges are given by mutation. This is called the exchange graph. Okay, so let's start. We started yesterday already. Yes, question?
Yeah, so could you please enlarge your screen? It's a, I mean, so the, yeah,
No, no,
it's
I will
still,
fix that. Yeah, it's not
oh,
about him. Maybe I will just stop spotlighting. Yeah, then it will be fixed.
thank you, thank you,
Yeah,
thank you,
okay.
thank you.
I do not actually see what you are seeing at this moment. Yeah. Is it better now?
It's okay, perfect.
Okay, that's good. Well, my screen is already at maximum size. Okay. Okay, good. So let's do an example of this procedure computing an cluster algebra. And we start with the simplest quiver that has any arrow at all. So let's take the quiver that has got one arrow, the quiver of type A2. Our initial seed is this quiver and two variables x1 and x2. And then we need to define what is a mutation. Let's mutate at 1, at the vertex number 1 here. And the mutation of this seed is given by the mutation of the quiver. The mutation of the quiver um, so we came up to here yesterday. So this is our initial seed. And let's do the mutation in 1. The mutation at 1 of this quiver, 1 is a source, so we just flip the arrow around. This is the mutation. This is mu1 of q. This is easy. And then to mutate the variables here, we mutate at 1. This means we keep x2, we write x2 here, and we only change x1, and x1 is given by such an equation. x1 prime is, and now there was the sum of the products of arrows leaving 1 or ending in 1. So there's exactly one arrow leaving in 1, and the end of this arrow is the vertex 2. Therefore, we write the cluster the variable x2 here. So this is this part here, the part x2 here in our formula stands for this one. This is the product over all u over all arrows starting in 1, and we take as index the vertex where the arrow ends. So this is exactly what we do here. You have to remember this formula because it's always going to be the same. There's one arrow starting in 1, it ends in 2, so we write x2 here. And the other part of the formula here deals with all arrows that end in 1, but there is no arrow ending in 1, so it's the empty product, and if we have the empty product, by convention we write 1. So this is how we mutate. And I would like to rewrite this. I would just solve this for x1 prime. So x1 prime is 1 plus x2 over x1. That's our new term. This is what we write here as our first entry. So our first, this is our x1 prime, and our new seed u1 comma u2 is made up of these two variables, these two rational functions. So very good. This is what we did already yesterday, right? And then we did the first start, but now we have to continue, and maybe you can go along with me. So I leave some blanks, and we did the mutation in 1. We have to, of course, do the mutation in 2. So we can do the mutation in 2 very quickly. This is rather symmetric, the quiver, right? So if we would like to mutate in 2, we first mutate the quiver in 2. Mutating this simple quiver is easy. I flip the orientation of the arrow, and then I need to mutate this set of variables. And if I mutate in 2 means I keep 1. Okay, let's do this. So the new set, the new cluster, the new set of variables will be x1, comma, and now we have to compute the x2 prime, right? And x2 prime is calculated in completely similar way. I need to apply that rule with an x2, so I change 1 to 2, meaning I will have a formula that reads like x2 prime equals something, or I can write x2 prime here as something over x2. And then what is in the so we know the denominator. What is in the numerator? In the numerator is the sum over all arrows that start in 2. Okay, but there is no arrow starting in 2. This gives me a 1. Plus the product over all arrows that end in 2. There's exactly 1. And this arrow that ends in 2, it starts in 1. So we write x1 here. This is how you do it. So the new variable here will be 1 plus x1 over x2. And that's it. Okay, so we slowly build up our exchange graph, starting from our initial seed, starting from the initial seed here. We already did 2 mutations, mu1 and mu2, and then we will have to continue building up our exchange graph. Yeah. So let's, it doesn't really matter, it's a very symmetric situation. So let's try to compute mu2 of this one. So here it starts getting more interesting. Yeah, we have to go through this once. Yeah. Okay, first things first, I want to apply mutation into to that seed. So I mutate the quiver. If I mutate this quiver, I flip around the arrow because there's only one arrow. Mutation will always change the orientation of the arrow. So the quiver is fine. Next thing, I want to mutate the variables. I mutate in 2, meaning I will replace x2, but I keep the first one. So I keep the first one, 1 plus x2 over x1. Very good. And then I compute a new one, which is again of the form x2 prime. Yeah. And x2 prime will be of the form something over x2. So I can already copy this. So this will be yeah, it's something over. Let's wait a little. This is some expression over x2. Can I do this calculation on the side? Do you see? I do my calculations here. Do you see that? Okay. So this will be of the form. The formula doesn't change if I consider all the products of arrows in this quiver that start in 2. There's an arrow starting in 2. This is very good. And it ends in 1. So I need to put in here the variable in this particular seed here. I need to put in the variable that has the label 1. That was the first variable. So I need to literally take this variable here and I put it up there. You see what I do? I take the first variable. And then I do plus product over all arrows that end in that quiver in 2, but nobody ends here, so this will be a +1. Good. Okay. Now let's simplify this. I have an x2 in the denominator. I see here an x1 in the denominator. I bring this down already, so this is x1, x2 in the denominator. And the fraction up here, let's bring it all on a common denominator. Then this looks like 1 plus x1 plus x2. Do you agree with my calculations? I shouldn't mess this up. This is okay? Okay, good. So this is the variable that we get at the end. So we do have 1 plus x1 plus x2 over x1, x2. So what are the cluster variables? I can keep track of the cluster variables. We got x1, x2, 1 plus x2 over x1. We got some more. I just calculated 1 plus x1 over x2, and we got 1 plus x1 plus x2 over x1, x2. And the clusters, I should also fill in this information. What are the clusters? We computed this cluster over here. So that cluster is the cluster given by x1 and 1 plus x1 over x2. And we also computed just a new cluster. This was 1 plus x2 over x1 and 1 plus x1 plus x2 over the product x1, x2. So we have so far 1, 2, 3, 4 clusters and 1, 2, 3, 4, 5 cluster variables. And we are not yet finished. So the exchange graph that we computed so far is this one, and we need to keep on mutating. So this one looks very symmetric to that one. So let's continue here. Let's do mu1 of this one and see what we get here. Okay? Good. Let's do this. I flip the orientation of the arrow, 1, 2. Then I do a mutation in 1, meaning I keep the second variable. I keep the second variable. So in the second place, I keep 1 plus x1 over x2. And I exchange the first variable. Good. For the first variable, I do my exchange. So let me do this here. The first variable will be called x1 prime. I do my calculations up here. This will be x1 prime, which is going to be 1 over x1. So this is 1 over x1. And then I mutate in the quiver, and I just look at all the arrows that end or start in 1, and there's only one arrow. It ends in 1, and it starts, of course, in the other vertex. So there will be one term which is trivial, and there will be one term which has as index the second variable. So the second variable is 1 plus x1 over x2. And if you allow me to simplify this quickly, this is going to be exactly this one. Good. So I got no new cluster variable. I got the same thing, 1 plus x1 plus x2 over x1, x2. And we computed our exchange graph up to here. Very good. So last thing is either starting here or starting there. I need to mutate once more. And I should have prepared this better. I mean, my picture already suggests that the circle closes here, right? I mean, this will be the exchange graph. The exchange graph will be a graph with 1, 2, 3, 4, 5 vertices and 5 arrows connecting these vertices. This is the exchange graph. So last thing I need to verify, if I'm actually, say, if I'm standing here and I do a mutation in 1, because I did the mutation in 2 already. If I do a mutation in 2, I just go backwards. If I go forward, the mutation in 1, then I claim I will end up here up to isomorphism. Up to isomorphism, I rearrange the arrows, or up to isomorphism of quivers, or up to reordering of the cluster variables. So let's verify this. Can we do this together? This is the last painful or beautiful calculation of polynomials. Okay, so we are here. We want to mutate in the first variable. We flip the arrow. This is the easy part. Now, what are we going to doing with the cluster variables? So if we flip the first variable, then I keep the second one. I keep the second one. The second one is already here. I keep it. Sorry, there will be some isomorphism applied, yeah? I do not keep the order. So when I close this exchange graph, I need to allow for some isomorphism taking place. So you see the variable which was in position 2 here, will end up in position 1 here. I make some flip, yeah? But we do consider those seeds up to isomorphism, up to reordering, okay? So this variable will stay here, no worries, that's good. And what happens to the other variable? The first one, which need to be mutated. So the first one is going to be computed as something called x1 prime, and this will be something 1 over this variable. So my calculation up here will change. I now have to compute 1 over this. So this is 1 over 1 plus x2 over x1. You see that? The variable which I mutate ends up in the denominator here. And in the upper part, I will do 1 plus the other variable. The other variable is this one. So I need to exchange, and I need to replace this 1 plus x1 plus x2 over x1, x2. So this is really the rational function that I have to consider. Yeah, let's do this really slow. Let's bring the upper part onto a common denominator. So how can I do this? So that will be something like over x1, x2. And I'm gonna have x1, x2 plus 1 plus x1 plus x2. I do my calculus of fractions correctly so far. That's good. And what do I have here? I have 1 plus x2 over x1. And now I want to simplify, okay? I can cancel the x1 with the x1 here, good? And then you observe that 1 plus x1 plus x2 plus x1, x2 you can factorize. Can you tell me what it is?
One plus
You
x
can-
times 1 plus x2.
1 plus x1 times 1 plus x2. Good, thank you. So I do in the numerator see a factor 1 plus x2, which I can cancel with the 1 plus x2 down here, right? So the final result will be finally we got the 1 plus x1 and we divide it by the x2 which I have here. So that's the final result, okay? So, and this is exactly what we have here. So we made no mistake. Very good. Thank you very much. Good. So up to some reordering of the variables and up to some isomorphism of the quiver. If I do mutate this one in 1, then I do get that quiver and I close the loop. The exchange graph is this one. Okay. Okay, so we saw a couple of important things that I would like to summarize in a theorem here. We have all cluster variables. We have 5 cluster variables. We have 5 clusters. I forgot 1, 2, 3, 4. I'm missing kind of one cluster. 1 plus x1 over x2, and that complicated one, 1 plus x1 plus x2 over x1, x2. Okay, and the cluster algebra is the algebra generated by the cluster variables. So the cluster variables are those, and I just take the commutative algebra, which is generated by those rational functions. Okay, so here was some little, if I miss up my calculations, I could cheat and look down here, but we got that right. Thank you very much. So What can we see from that calculation? Theorem, Fomin-Celibinsky. Fomin and Celibinsky already proved in the general context of cluster variables over quivers or over valued quivers over skew symmetrizable matrices. They did observe that every cluster variable is a Laurent polynomial. What is this? A Laurent polynomial is a quotient of a polynomial divided by a monomial. So every cluster variable is a Laurent polynomial with integer coefficients. And look, this is not completely clear from the outset, because you saw here that in the calculation of our variables, we sometimes divide by rational functions. So a priori in the denominator, we could have some polynomials, yeah? So a priori, that doesn't look like a monomial, but luckily that monomial, that polynomial canceled out with a factor that was sitting up here, yeah? And Fomin-Celibinsky prove this is always happening, yeah? So we always end up with a monomial in the denominator, yeah? So when we do our cluster mutations, a priori there are some polynomials appearing in the denominator, but they always cancel out, and we always have only monomials in the denominator. Our monomials in the denominator here are the monomials x1, x2, and x1, x2. Simple as that, yeah? There's no actual polynomial. The polynomials are in the numerator, they are here, yeah? Okay, so this is the first observation, the first theorem that they proved. The second part of the theorem, the number of cluster variables is finite precisely if and only if the quiver we start with is mutation equivalent to a Dünkin quiver. So that kind of extends Gabriel's theorem a little bit, because we allow now a more complicated version of reflections. We allow mutations at vertices that are not a sink and not a source. So our quivers are a priori a little bit more complicated. For instance, we could consider, for example, a quiver that looks like this: 1, 2, 3, 1. Which is not a Dünkin quiver at all, yeah, but this quiver is mutation equivalent to the quiver 1, 2, 3, if I mutate in 2. And this one is a Dünkin quiver, so that is Dünkin, and therefore the quiver Q prime here defines also a cluster algebra which has only finitely many cluster variables, yeah. So we extend a little bit the Dünkin quiver to the set of quivers which are mutation equivalent to a Dünkin quiver. So in all of those cases, we do get finitely many cluster variables. And then finally, this is the refinement of Gabriel's theorem. Finally, oh, I see a question. Do I mean simply lace Dünkin quiver for the part B? I do not mean simply laced. I mean, their theorem was really for general root system or more generally for root systems, or B is a skew symmetrizable matrix, which is mutation equivalent to some B prime, where B prime is of Dünkin type. And here I mean all Dünkin types, A, B, C, D, E, F, and G. Yeah, so they proved their theorem in the general context of valued quivers and root systems.
So may I ask a question? Sorry.
Yeah.
So in A, did you mean positive integer coefficients? Because we saw that Laurent monomials, they have positive coefficients. or only
This is a
integer
very,
coefficients?
yeah, this is a very good question. It's actually a very complicated question, and I will address this in a minute, okay?
Sure, thanks.
So first, let me finish the main results. So these are the results that they proved in their very first paper. So the last part, second part is finite type cluster algebras corresponding to Dünkin types, yeah? And then if you are Dünkin type, Gabriel, in Gabriel's theorem, the classification of representation finite quivers, this is that the representation finite quivers are the Dünkin quivers, and moreover, if the quiver is Dünkin, the number of indecomposables corresponds to the number of positive roots. You have seen this in week 1, right? Can I tell you a little story? Do you want me to tell you a little story? So Gabriel announced this result in Oberwolfach. Oberwolfach is a mathematics research center in Germany, where year-round mathematicians gather to discuss their latest results. So that was in the 1970s. There was a Oberwolfach meeting, and Gabriel announced the result, the classification of the representation finite quivers. These are exactly the Dünkin quivers. And then he calculated the number of indecomposables. So I have to tell you that Gabriel's first original proof, I mean, you discussed a proof of Gabriel's theorem in week 1, which was using reflection functors, right? And the use of reflection functors is motivated if we look at what happens on the Lie algebra side. There are the reflections, the Weil group elements, they act on the positive roots, and we kind of mimic this action by reflection functors. So from any simple root acting with reflection functors, we can compute all the other roots, and under reflection functor, the dimension behaves like the like the action in the Weil group. So there's a nice bijection between these two things. Now, this was not Gabriel's original proof. Gabriel's original proof was based on matrix reduction techniques, which was at the time done in 1968, so a few years before, in Kiev, in the Kiev School of Mathematics by Reuter and Nazarova. And they computed matrix problems given by posets, and they came up with lists of finite type matrix problems, and then they classified all the indecomposable matrices. So Gabriel had huge lists and papers which they gave him, and then he would just sit down in type A. Okay, he added everything up. You get so many. In type D, you get so many. In type E6, you get how many indecomposables? This was a question to the audience. How many indecomposables for type E6? You need to remember this by heart. There's 36. There's 36 positive roots for type E6. Yeah, E7 has 63 and E8 has 120. Okay, remember these numbers. And so Gabriel put down together all these indecomposable matrices that were given to him from the Kiev school, and he added them all up, and he came up with these numbers 36 and 63 and 120 for the E types, and some formula for A and D types, and he presented this in Oberwolfach. And as always, he was very he prepared his lecture only in the night before. He probably did not sleep, as far as I know him, and then he presented these numbers, his theorem and the numbers. And then Jean-Pierre Serre was in the audience, and Serre he was formerly his supervisor at the École Normale in Paris. So Serre raised a question, and he said, but Pierre Gabriel, he said, these numbers are exactly the numbers of positive roots for the corresponding Lie type. So apparently, this is the story. Apparently, Gabriel was not aware that these are the numbers of positive roots in the corresponding Lie type, yeah. And only afterwards, when people realized, there must be a closer connection, this cannot be a coincidence. There's no coincidence in mathematics. So only later people then thought, well, okay, how can we connect this? There's the while group, there's the action of reflections. Can we mimic the same game on the representation theory side? And then they defined those reflection functors and observed they behave in the same way. And then obviously, yes, starting from the simples, you create the same numbers. Yeah. So that came only afterwards. Yeah. Okay, this was my story. Thank you very much. So let's come back to the cluster situation. So if we are in the Dünken type, we want to see some connection between the cluster variables which are finite. This is the gadget that we measure its finiteness. Yeah. So this finiteness is related to which number on the Lie theoretic side. So they observed, Fominenz and Lewinsky observed that the number of cluster variables is in bijection. It's the same number as the number of positive roots plus the number of negative simple roots. Okay, so there's more cluster variables than positive roots, and in fact, we do have the initial cluster variables. So we do have the initial cluster variables which correspond, okay, we do have the initial cluster variables which correspond to those negative simple roots, and then we do have the non-initial cluster variables, and they really correspond to the positive roots. So let's verify that in our example. We computed a nice example here, A2. We know everything, yeah, we know all the cluster variables. There are finitely many, 5. Okay, so 5, very good. We have 5 cluster variables. 5 is 2 plus 3. There's 2 simple and 3 positive roots. And you remember, let me go back to the root system of type A2. So there's 3 positive roots, the 2 simple ones and the sum of the 2 simples. These are the 3 positive roots. Okay, you have this in mind. Good. So we are in type A2. We are in type A2. We have 5 cluster variables, 2 simple and 3 more, and the 3 more correspond to the positive roots. So the first cluster variable, which is not one of the 2 initials, is this one, the second is this one, the third is this one. Now, how can I relate them to the positive roots, alpha 1, alpha 2, and alpha 1 plus alpha 2? You look in the denominator, yeah? The denominator has 1 copy of the first initial variable. I would like to relate this to alpha 1. In the denominator, you find a copy of x2, so this should correspond to alpha 2. And in the denominator, you see x1, x2, so that should correspond to both of them appearing. So that should correspond to the root alpha 1 plus alpha 2. Yeah, so this is in fact the bijection in part C of the theorem. The bijection is really given in this way. We do write our cluster variable as a Laurent polynomial, meaning in the denominator we have only monomials. The monomial is gonna be a power of the initial variables with some exponents d1 up to dn, and then we relate this variable x to the root, which has got exactly these numbers of the simple roots appearing. Yeah, this is exactly the formula we have here. You see what we do? x1 times x2 corresponds to the root alpha 1 times alpha 1 plus 1 times alpha 2. Okay. And that formula really translates to all the other Dünken types. So if we are in type C2, we could compute the cluster algebra. So in C2, we have a root of the form 2 alpha 1 plus alpha 2. So in that case, there must be some cluster variable, that one should correspond to some cluster variable which has got x1 squared, x2 in the denominator, and some polynomial upstairs. Yeah. So this is really how the bijection works. Okay. And sorry, I got a bit of a cold. I need to drink something. You can kind of force this formula still be true for the initial variables. I mean, if I cheat a little bit, I can write x1 as 1 over x1 to the negative 1, if you allow me to do so. And then the exponent would be minus 1, so this should correspond to the simple root minus alpha 1. You see what I do? I'm a little bit cheating here, okay? I want to force this formula to be true, like always. Good. So that's how the bijection here works. And we verified the bijection in this simple example type A2. So you should by now be convinced this works well, this is true. That's okay? Okay, thank you very much. So we got some more questions that the polynomials, they all have positive coefficients. So the mathematician in you ask the question, but do they count anything? So when the mathematician sees positive coefficients, then we are like, they must count some combinatorial gadget, right? And they do count certain things. There's a lot of research going on into this direction. But let's first verify that everything is actually always positive. And this is a big theorem. This is the theorem that I would like to formulate next. So this is the positivity theorem. One of Fomin-Seliwinski's original motivation was to show certain kind of positivity when you express those initial cluster variables after some mutation, you get positive expressions. And that is the result. Every cluster variable is a lower polynomial in the initial variables with coefficients which are natural numbers. Yeah. There are no negative numbers appearing in the coefficients. So we formulated everything above. These are lower polynomials with integer coefficients. In fact, these are positive, non-negative integer coefficients. That's a big result. So that was conjectured by Fomin and Seliwinski because they computed some examples and they saw always only positive coefficients appearing. And then there was a long history. There are partial results by many people. Leclerc, Chin, Nakajima, Musica, Schiffler, Williams did it in the context of cluster algebras coming from surfaces that I would like to discuss later in the week. And the full proof was given by two groups. One is Lee and Schiffler. They did a kind of a brute force combinatorial proof. And the other one was by Kontsevich Seubelmann, which used sophisticated techniques from theoretical physics. This is a complicated result. So listen, you might be tempted to say, but isn't this trivial? I mean, we start with with x1, x2, xn, with the initial variables. What is our mutation formula? How do we define the new cluster variables? Our mutation formula is this one. There's only positive coefficients appearing anyways, right? I mean, what is u1 uk prime? This is 1 over uk times 1 times this plus 1 times this. So there are only positive coefficients. So where's the problem? The problem is that in computing the cluster variables and in writing them as actual lower polynomials, we do some simplifications. Yeah, we divide, we simplify those polynomials. We do some factorization, right? And in general, in general. So where's the problem? Why is this a surprising result? The mutation formula has no negative coefficients to start with, but we do simplify the quotients of polynomials. And in general, if you have a quotient of two polynomials, all have positive coefficients, the quotient might have negative coefficients. Yeah. So if you give me two general polynomials like this one and that one, you factor the upper polynomial as x squared plus 2x plus 2 times x squared minus 2x plus 2. It is not at all clear that in our simplification process we never get negative numbers. Yeah, a priori this could happen. You see my point? So that result is in fact a complicated result, and it took really 15 years to prove it in full generality by many people. Yeah. So this positivity is a important result, and in proving the positivity result, people started. I come back to the question in the chat. People started interpreting the coefficients that appear in these polynomials as counting things. Yeah, and in Musiker, Schiffler, Williams, this is cluster algebras coming from surfaces. They were counting curves between 2 points going in different directions, and they were counting partitions of certain combinatorial objects that they associated. So they count stuff. As soon as you count things, then these are positive numbers. Yeah, but it was very complicated to establish this result.
I have
okay.
a question.
Yeah. Yeah. Sure.
Regarding the citation. So I believe Lee and Schiffler is for quiver, but for valued quiver, the full proof was gross hacking kill Concevich. Or
Yes,
is
yes,
it
yes, yes,
Concevich
yes, yes.
Silverman?
Yes. So Lee Schiffler did it for quivers, and for the full general version, there's also cross hacking kill. Cross hacking. Sorry, I should write this in black. So the last very general result is cross. What did you say? Cross hacking kill Concevich?
Yes. They did it for valued quivers, I suppose.
Yes. This is the most general result.
And what was Concevich Silverman's one?
I thought they had some preliminary version of that.
I see.
But I would need to verify, yeah. But the final result is cross hacking kill Concevich. Yeah, right. Thank you very much.
Thank
you.
But
Thomas,
this yeah.
Any motivation behind the mutation formula, like how to write the new cluster variable in terms of the old ones, like sums of products, the sum of two products?
Yeah, I cannot really. I can. I give you maybe my next example answers your question.
Okay.
So because I mean right now, coming back to the cross hacking kill Concevich, this is a really complicated paper. Do you agree? Who brought this up?
Yes, I tried reading it, but I couldn't.
It is really complicated, yes. I do not recommend reading it if you no, you should read it, but it's really complicated. Sorry. It's a complicated result. Let's keep it like this. So Amit, good question. I mean, why we verified they come up with a complicated rule, a complicated recursive rule. And in the recursion process, in this formula, the quiver or the matrix enters because we compute which arrows appear in the quiver, but the quiver is also changing. So we do a very complicated recursion. I mean, we do recursion. Each recursion step is we mutate variables according to some quiver, but the quiver also changes along the process. So it's a very complicated process, yeah. And why would they come up with such a thing? And we verified in type A2, yeah, okay, this is what we get. And I would like to discuss in the tutorials A3, and I would like to discuss it just to show you it's really, really complicated, yeah. And why would we do such a thing? So the question is a bit, do cluster algebras appear somewhere in nature? I mean, is this a natural thing to do? I cannot really motivate at this moment this formula. Maybe we will later see with the combinatorics of cluster algebras, of cluster categories, that it corresponds to certain things in the category of representations, yes. But at this moment, it's really not clear why that is a good formula. So we ask ourselves the question, do cluster algebras appear elsewhere? Okay, and they do appear elsewhere. So I would like to address this question. Do cluster algebras appear in nature? Of course, this is too much asking. Do they appear somewhere in mathematics? Yeah. And I just would like to mention one particular example. And this one is a very classic example. This is the example of, of the coordinate. So let's take the algebra A, which is the coordinate ring of the Grassmannian. The coordinate ring of the Grassmannian 2n plus 3. So it's the coordinate ring of the algebraic variety of planes in a space of dimension n plus 3. Yeah. So planes are given by two generating vectors. Yeah. Every plane is spanned by two vectors. So whenever two vectors in n plus 3 dimensional space span a plane, this is going to be one point in this Grassmannian. This Grassmannian has a structure of an algebraic variety. I don't go into this. An algebraic variety has a coordinate ring, and this is what we are interested in. Now, turns out this is a very, very classical subject. This is 19th century mathematics. This is 150 years old, and or more than that. And in the 19th century, a German mathematician, Blücher, showed that this very classical ring is generated by variables which he labeled xi, j, where I and j is an ordered pair ranging from 1 to n plus 3. So these are the variables generating this ring, but it's not freely generated. They satisfy some relations, and they satisfy what is called the Blücher relations. And Blücher relations are relations of this form. Whenever you have a quadruple I, smaller j, smaller k, smaller l, then you do have the relation, the Blücher variable x. The product of these two Blücher variables, xik, xjl, equals the sum of two other products of Blücher variables, as you see here. Yeah. So that's very classical algebraic geometry result. Okay. And I want to tell you, and this is what Fomin and Seliwinski also observed, that we can reinterpret this in terms of cluster algebras. So the Blücher coordinates will correspond to cluster variables, and the Blücher relation will be an exchange relation. It doesn't work totally smoothly. So of those Blücher coordinates, we want to specify some of these polynomials to 1. Yeah, so if I set the Blücher variables of adjacent index, so xi, I plus 1, if I specify all of them to 1, then I get a subring of this. Yeah, so certain of them I specify to 1. Then what I do get is that this algebra where I should add, where we specify all xi, I plus 1 to be equal to 1, then this algebra is actually a cluster algebra, and it is the cluster algebra of type AN. So one of the very first quivers that you can think of appears actually in the coordinate ring of a Grassmannian, which is a very natural subject in mathematics. So I mean, I don't know if this really answers your question, but kind of those kind of relations, those kind of
Yeah.
exchange relations, they are very classical. They do appear in algebraic geometry. So this is not a total surprise.
Okay.
That's okay.
Yeah.
And let's verify this for our case. What did we do? We have A2. Yeah. So let's say n equals 2. This is the only cluster algebra we know so far. So this is our calculation here, right? So let's do A2. We know what are the cluster variables. We know the exchange. We know everything. Okay. So let's try to look at these Plücke coordinates when we are in the case where n equals 2. So n equals 2, A2, this is this. We have the Plücke coordinates. So we want to specify x1, 2, 2, 3, 3, 4, 4, 5, 5, 1. I do this cyclically, yeah. So I go modulo whatever, modulo 5, yeah, modulo 6. So I will specify all of those to be equal to 1. And then the remaining Plücke coordinates are those given by a set of indices whose distance is more than 1. And the exchange relation, the Plücke relation, is then, for instance, of this form. Yeah. So first, how can I remember this? Yeah, I mean, that looks like a bit painful. There's a nice geometric model. How can you remember that? There's the model given by a polygon. So let's just, for the moment, this is just a play, this is a game. Let's fix a polygon with vertices 1, 2, up to n, cyclically oriented. And let's say we have 4 indices, 1, smaller j, smaller k, smaller l. And then the Plücke relation, I just copy the Plücke relation from here down into this picture. What is the Plücke relation saying? The Plücke relation is the following. When I take the product of the two variables, which correspond to the diagonals, I mean, variables are given by ordered pairs of vertices. So every variable is given by a diagonal in that polygon, right? Every variable is labeled by 2 points in the polygon, and I label them 1 up to n. So when I take in a square I, j, k, l like this, when I take the product of the two crossing diagonals, this one, this equals to the sum of the products of the two opposite sides of the rectangle plus the product of the two other opposite sides of the rectangle. This is how I can remember the Plücke relation. Okay, this just helps me at this moment remembering the Plücke relation. Okay, product of crossing diagonals equals the products of the variables on the sides of the rectangle. Good. Okay, so now let's say I want to bring this I want to compare this to our cluster algebra A2. Our cluster algebra A2 had two initial variables, x1 and x2. So we have our cluster variables, which we can visualize as diagonals here. Our cluster variables, we know them. There's two initial cluster and 3 others. Yeah. So the two initial cluster variables, we need to make a choice. Let's say x13 is the first initial and x14 is the second initial. So I do choose x13 and x14 as my set of initial variables. Good. And then we did our mutation, right? So our mutation was, for instance, what was our mutation? Say we want to mutate x1. Yeah, so if we want to mutate x1, then we say x1 prime, the mutated variable, this was 1 plus x2 over x1. This was this one, right? And or I can write this otherwise, x1 prime equals 1 plus x2. And how does this compare to our Plücke relations? Yeah, our Plücke relations are saying that, where did I specify? I have this exchange relation here. Sorry, this is our Plücke relation. Let's say we have x, where are we? We have x1, 3 times x2, 4. These are the two blue ones in my picture, sorry. So x1, 3 times x1, 4. These are the two initial cluster variables, x1 and x2. And then the Plücke exchange relation tells me this is going to be this sum. Yeah, so this is going to be x1, 2, x3, 4 plus x2, 3, x1, 4. But you, I mean, you see that x1, 2, this is one that we specified to 1. This is one of the form xi, I plus 1. x3, 4, this is what we specified to 1. Yeah, so really the formula gives me x1, 3, x2, 4 equals 1 plus, and x2, 3 also was specified to 1. So this is really 1 plus x1, 4. Okay. And I hope that kind of works out with my formula. x2, 4 is 1 plus x1 for x3. So if I specify x1, 3 is x1 and x1, 4 is x2, then this is really the exchange formula. This is really the exchange formula. x1 prime equals 1 plus x2 over x1. So it fits well with our calculations before. This is really, if we specify those xi, I plus 1, 2 equal to 1, then the Plücke relation corresponds exactly to our cluster relation. It's the same thing, yeah, to the cluster exchange relations. Okay, this is good. So that geometric model I want to explore quite a bit later in the week. Because this gives us a good source of cluster algebras, and sometimes you can memorize, you can understand those exchange relations better if you have some. I can do it, remember it better if I have some geometric model, something that helps me remembering these mutations. Okay. Okay, good. So now that kind of ends the first part, and what I want to do next is I want to come back to representation theory. We did spend a lot of time in the first 2 weeks considering the category of representations of a quiver, or more generally representations of algebras. And there is a model, there's a after cluster algebras were considered by Fomin and Seliwinski, and many people started looking at that, they have the result that the finite cluster algebras correspond to Dynkin quivers. So people from representation theory got interested in the story. Yeah. So there's Gabriel's theorem, which classifies the representation finite quivers. There must be some relation between those cluster variables, which are finitely many, the initial ones plus the non-initial ones, which correspond to the positive roots. So they correspond to the indecomposables of the corresponding quiver. There must be some relation. We must be able to realize the combinatorics of cluster algebra. We must be able to realize the cluster variables using representation theory. So there started a big research investment into trying to model that combinatorial rules using categories of representations. So this is what I want to start now. Yeah, that will we will spend quite some time on how can we model cluster algebras using what we studied in the first 2 weeks. Representations of quivers, categories of representations of quivers. So I want to start with the simple case where Q is a Dünken quiver, everything is finite. And I will develop much of the theory for Dünken quivers, and then eventually I will say certain parts can be generalized. Okay. So the thing is that going into those cluster algebras, what we see from the result, from the very first result of Fomin and Zeliwinski in part C, for the Dünken quiver, there's a bijection between cluster algebras, 2 positive roots plus some more roots. Yeah, so there's more cluster variables than there are positive roots. Positive roots are in bijection with indecomposables of the quiver, so we need to enlarge our category. This is what I want to tell you in the beginning. Yeah, if we only look at representations of Q, we only see this part, but we want to have a larger picture where we can include this one. So we have to enlarge our category of representations to some larger gadget. Yeah, and there is a category which is studied in representation theory, which contains the category of representations, and this is called the derived category. And the definition is a bit complicated, so I want to do this very carefully, and I will not give the full definition, but just in that simple case, we can realize it quite easily. So I kind of try to define derived categories now. Among the audience, who knows derived categories? Can you give me in the chat a quick yes, I have seen it, or no, I don't know. Amit knows derived categories. So I see 1, 2, 3, 4, 5, 6, 7 people. Seven people say they know or they have seen derived categories. Thank you very much. Out of 28, so that's not a lot. So I will introduce derived categories, but kind of easily. Okay, good. So let's start like this. We have given a Dünken quiver. What you can form first is the repetitive quiver. So we continue, we want to give ourselves Z copies, as many copies of the quiver Q as there are numbers in the integers. So for the vertices, we just take pairs where P is an integer and I is a vertex. So we really our index set for this quiver is really the integers times the vertices in the quiver. And then arrows, whenever I have an arrow in my given quiver, I have an arrow in this copy number P, which I denote by P comma alpha. And then we want, for every such arrow, we also want to give us another arrow which goes between the copies. So there's going to be another arrow from copy P minus 1, but I reverse the direction. So if alpha goes from I to J, I go from the copy P minus 1J to the copy P comma I. So let's do this in a simple example. Can you see down here? Okay. So I start with my quiver 1, 2, 3 and 2 arrows alpha beta. And then I just give myself a copy of 1. So I give myself a copy 0, 1, 0, 2, 0, 3. And I get these 2 arrows 0 alpha, 0 beta. And I do this for every integer. So I have 1, 1, 1, 2, 1, 3, and a copy of these. So I literally give myself copies of these things, like infinitely many, and I just I just change the labels 0, 1, 2, and so on. Yeah. So for every integer, I give myself a copy of the quiver. 3, 3, 3. Sorry, this is a bit messy. So I continue this to the left and to the right. And then what about the arrows? So there's one arrow, that's what we said. There's for every arrow here, I give myself one copy of this arrow throughout all integers. That's good. But then I also add a copy between the preceding I also add one arrow between the preceding copy and reversing I and j. So what is this going to be? I will introduce such a copy. Alpha, yeah, the arrow alpha induces an arrow between the copies from 1 to 2, but it also induces an arrow in the other direction from the preceding copy. So I'm gonna have arrows like so from alpha, and I'm gonna have arrows like this from beta. So that's the whole quiver. Okay? So as a final result, this is how my quiver looks like. Yeah. I get a nice band, and I do not really see my original quiver in the beginning. It was like this, and then I built it up doing these copies, but this is kind of hidden in the final result. That's what my quiver looks like. Okay? Good. Now this quiver, I won't always be there to be a translation in this quiver. So you see my blue dotted arrows. I want to denote this as the translation in the quiver. So there's going to be a translation operating on this quiver. There's an automorphism denoted by tau, which just moves the vertex at point pi to one copy before p minus 1i. So tau moves one step to the left. Good. So this operates on the quiver. And okay, now I come with my general machinery. I mean, you have seen the category of representations of Q, or if you prefer, this is the equivalent to the category of modules over the path algebras KQ. This is the category of representations. This happens to be an abelian category, and for an abelian category, one can define something that is called the derived category. This has been done by Verdier, who was a student of Grothendieck, like Gabriel. And this derived category, the bounded derived category of the category of representations of Q, I will denote by dq here. And in our situation, result by Happel 1974, Happel introduced really derived categories to representation theory. Happel showed that when we start with a Dünken quiver, then the Ausländerreiten quiver of this derived category is that one ZQ, which can be kind of defined easily combinatorial like so. Yeah. What is the Ausländerreiten quiver of the derived category? It is the quiver whose vertices are the indecomposable objects of the category and whose arrows correspond to irreducible morphisms between those indecomposables. Yeah. So this is the picture of the derived category in the sense all the vertices correspond exactly to all the indecomposable objects in the derived category. And morphisms, there are morphisms whenever there are arrows or compositions of arrows. So the arrows correspond to morphisms that cannot be factored through other morphisms. They are irreducible, and all morphisms are obtained by composing those arrows. So this kind of describes the whole category. And moreover, I have like 15 minutes.
Yes, yes.
Okay, good. So I can go deeper into this. Very good. So far what we know is this derived category, which I didn't explain you what it is in the case of a Dünken quiver, can easily be described using that infinite stripe where we have iterated copies of the original quiver. So that's fair enough. And now, the derived category is the derived category of a category of representations, and this one is contained in here, so we want to see it inside. Yeah. So the Ausländerreiten quiver of the category of representations. I mean, you did discuss the Ausländerreiten quiver of representations of Q, right? So this Ausländerreiten quiver is a full convex subquiver of this quiver set Q. So the Ausländerreiten quiver of the category of modules or representations will be a full convex subquiver of our quiver ZQ. And the vertices of ZQ are obtained if we take the vertices of these category of representations. But for a Dünken quiver, that's going to be a finite set. Yeah, Dünken quivers are representation finite. This is a finite quiver. But then we start shifting this by a certain amount, and we shift it infinitely to the left and to the right, and we take the union of all those copies, and this is how we get ZQ. So this is something that I have to explain you. So let's do the example A3, which I believe is complicated enough, yeah, to see what's going on. So for the example A3, we have, I hope you have all seen what are the indecomposable representations. The indecomposable representations are given by that Ausländerreiten quiver. So there are, for every vertex, there's a projective P3, P2, P1. We start the Ausländerreiten quiver with the projectives on the left. And then there are some more indecomposables. The simple representation in 2, I1 is injective, but this is also equal to the simple representation in S1, and P3 is the simple representation in 3. And then there's only one more representation, this one here. So this one completely describes the category of representations of A3. This is the Ausländerreiten quiver of the category. And now, how is this embedded into ZQ, into the derived category? So we see that triangle can be embedded like so. You see that? I can do this. Yeah. So I see that this triangle, I see the category of representations be a full convex subquiver of this infinite stripe. Very good. And then I want to fill, I really want to fill ZQ by copies, by disjoint copies of that part. So if this is a triangle like so, I have to flip my triangle and fill it in here. You see what I do? Yeah, if I want to cover my whole stripe, I have to iterate, flipping the triangle and go to the left and go to the right. And like so, I can cover my whole stripe ZQ. Do you see what I'm doing? So this is possible, and Hubble guarantees us this is always possible for every Dünken quiver. And in fact, you can always cover the whole derived category of a quiver by copies of the category of representations. This is always possible. Good. So to fix some notation, this one is the category of representations. This is sitting here. I need to make a decision. I say, I put this here. Yeah, this is a random decision. Put this somewhere. And then the next copy, this flipped copy, that one here, I call this rep Q1. And then comes rep Q copy 2, and here's rep Q copy -1. So this is rep Q shifted 0 times. This would be shifted -1 times, shift 1, shift 2. So the shift functor moves this object here. Yeah, so there's a certain shift going on, and the shift functor would move the object x here to this place, x1. You see what I'm doing? The object y here would go up here, y1. And if I move x1, if I want to shift x1 one further, then I go to the next copy. So this one here would be x shift 2. So this is how the shift operator acts on that infinite category ZQ. And the shift of operator is strictly different from this operator tau. Tau moves one step to the left. Yeah. So I've got a shift, which is this funny operation, and I got an operator tau, which goes one step to the left. So these are the two operations that we have on this category. Are you okay so far? Do you have any questions?
The tau shifts are flips, the triangles.
Excuse me, could you? I didn't get you.
No, the tau, whether shifts are flip the triangles.
Yeah, this is a funny thing to, if you want to cover such an infinite strip by triangles, you have to flip the triangle. Yeah, I mean, you do some puzzle. I mean, the only way to cover the whole strip by triangles is that you flip the triangles, right? You see that. But the tau is very symmetric. Tau just goes from. I mean, how did we originally build? There was Q copy 1, Q copy 2. The tau goes just from this to that copy. Tau always goes to the left. Tau doesn't flip.
So in the netting procedure, we usually stop when we get a negative entry in the dimension vector. So here we are allowing all possible integer vectors.
I will get to this. Yes, totally right. Yes, I will get to this. So this shift map here, this shift map mapping x to x1 is called the shift or the suspension, and we saw, okay, yeah, so we saw what the shift is doing so here would be p3 1, and here would be p3 2, and so on. Yeah, so this would be s2 1, etc. So before, yeah, so I would slowly like to get to the knitting procedure. The numerical properties of the Ausländerreiten quiver are some of the numerical properties of the Ausländerreiten quiver are the following. So when I have two objects, two modules, two representations m and tau m, so like so there would be m and there would be tau m, like two objects, this one and this one. So this could be m, this could be tau m, and then I have these direct successors of tau m, and I have the direct predecessors of m, and these two sets coincide. Yeah, so this is one of the numerical properties of the Ausländerreiten quiver for modules. So if I have a set of the set of direct successors of tau m coincides with the set of direct predecessors of m. There's a symmetry. These two are equal. And this one is an Ausländerreiten sequence. It is a short exact sequence, which means it is additive on dimension vectors, which means if I sum up the dimension vectors of the n terms, I do get the sum of the dimension vectors in the middle. So this is this formula. The dimension of m plus the dimension of tau m equals the sum of the dimensions that you have here sitting in the middle. This is one of the numerical properties of the Ausländerreiten quiver. And you can see, you can verify this for the Ausländerreiten quiver of 1, 2, 3. If I look at the dimension vectors, this is the simple in 1, 0, 0, 1. This S2 is the simple in 2, and P2, the projective in 2, starts in 2, so the dimension vector is 0, 1, 1. And the sum of these two n terms is the term in the middle. So this is the additivity along Ausländerreiten sequences. You have seen this? Yeah? Okay, very good. And this is what Amit was saying. So the same formula applies to the derived category. just when you did the knitting procedure before, I mean, we can do knitting here, and then you said, if I apply knitting to this triangle, what would I get? Yeah. So I say that one is 111, this one is 101. So what would the knitting procedure give me if I were to compute the vector here? The vector here would be the middle term 110 minus the starting term minus 111. So that would be the vector 0, 0, -1. So in last week, in the knitting procedure for modules, for representations, you would said, we stop here. We stop the process because there's no module that has a negative dimension. This makes no sense. So the knitting procedure for representations would just end here. Now, in the derived category, I tell you, you are allowed to continue, but keep the same formula. So this object here has attached some value, 0, 0, -1. You should not interpret this value as an actual dimension of anything. It just fits the numerical formula, and it kind of indicates if I have the one copy of representations here, and here I have the shifted copy of representation, the next shift will come with negative signs. Yeah. So I have the copy with positive signs, then I do produce the exact same numbers, the exact same dimension vectors, but they all come with negative signs. So in this derived category, I do allow fancy objects which are not representations, but the numerology, they follow kind of the same formula, but I do allow negative entries in the kind of dimension vectors. Yeah. So I have the 0 copy, I have the copy number 1. If I shift again, I fall back to positive entries. So this is positive, negative, positive, it alternates. Okay. So this is the message that the same knitting algorithm does apply to the derived category, just you just continue. So where you stopped before because there's a negative number, you just keep going. Yeah. Don't be afraid of the negative numbers. That's the message. Okay. So this is what we said, that this formula here allows to compute dimension vectors of the indecomposables recursively. And since the dimension vector determine the indecomposable for drinking quiver, we really do get all indecomposable representations. This is what you did last week. So if you assume that you know already tau m and you know all the direct successors of tau m, then you can compute the dimension vector of m as the difference of these two. These two are known, so you know the dimension of m, so you determine m, you can move forward. So this is the knitting algorithm. And the knitting algorithm goes from left to right through the quiver. You have done this, right? Yeah. Yeah, so this is very good. So I would like to just tell you what we do next, and then I stop. So we do know how to, by this knitting algorithm, we do know how to produce all those indecomposables. And next, I want to tell you there's a corresponding version of the knitting algorithm for cluster variables. And in fact, you can compute the cluster variables in that example using some similar knitting formula where you look at ingoing arrows and there's some formula. If you know these two, you can compute the third one. If you know these three, you can compute the fourth one. So there's a kind of a knitting algorithm for cluster variables, which I find kind of easier than using the original definition, this one. Yeah, so this is what I want to do tomorrow, kind of knitting algorithm for cluster variables, and it is motivated by the knitting algorithm for representations. Because after all, they should correspond to each other, right? Okay, good. Then let me end here.